Hello, everyone. Today's lecture is to talk about how machine learning is different for modeling or developing predictive models for materials, in particular with a focus on inorganic materials. This will differ a little bit from the molecular machine learning we've learned before, and hopefully in a way that kind of expands your picture on how you can use supervised learning for many different kinds of materials problems. Now, knowing that most of you are not materials engineers, we'll start off a little bit on why or what the word materials means to me and how that's different than just describing, say, molecular chemistry or molecular engineering. And what particularly separates materials, in my view, is the need to understand how the larger scale structures of a solid or a liquid influence its overall properties, and also how one processes the material to achieve that structure, which is commonly viewed with this so-called materials tetrahedron, which also includes the performance, which defines how the property and structure dictate how this material will actually function for an application. And to give an example of this, we can look at designing pharmaceuticals. And when you're considering how I deliver a medication, you also have to consider how I take that therapeutic molecule and form it into a pill, which is all kinds of questions about, okay, what do I mix it with to give me the right crystal structure such that it will dissolve? How do I go about processing it and how will that, say, affect how it's digested? And taking all of these different processes into account is really the core of materials engineering. Being able to control those different dials to be able to have that material act in a way that you need it to. So considering that our materials, when we think about them for machine learning, are multi-scale, you can really run into problems where you have to take many different types of information into account when modeling a material. So when I say think about inorganic materials in particular, you can imagine kind of a range of different types of data that you might encounter. Say you have a problem where you're trying to predict the mixing enthalpy of a dopant inside of another material. Here, the only bit of information that describes how different entries in your training set are different is just a single element. Additionally, you may be trying to, say, predict how two different elements mix, which is describing a phase diagram, or it could be all the way up to how are materials different based on not just their elemental composition, but what kinds of micron scale structures they form. Say, how do these iron particles aggregate within a steel alloy? What other phases are present along the edges of those grains? And all of that can be important information that you need to use to predict a material property and therefore incorporate into a machine learning model that can help you design that material. So if I'm thinking about inorganic materials, we'll look at these kind of first three types of data you may encounter first. That is, looking from data that are separated by elements all the way up to compositions, which are defined by different elements present and their relative ratios. And the one common way that's been done to or used to model such materials over the years has been to consider the properties of those different elements. Where if I look at a paper from Bryce Meredith and Chris Wolverton in 2014, they were found models to predict how different elements will dissolve in zirconia, a very important material for applications like thermal barrier coatings in jet engine alloys, and found that if I look at, say, the size of the oxygen in the oxide formed by that element, that can tell me which materials are better dopants, say for SMP block elements. Different kinds of elemental properties are important for, say, other kinds of elements. But at the end of the day, it's really those kind of single element properties that can be used to predict the overall behavior. Techniques going back at least 30 years for predicting the properties of phase diagrams, such as this work by Villers, where they use difference in melting temperatures and pseudo-potential radii, which have to deal with how large the core electrons are in a particular element, can be used to predict which or how these compounds will mix, say whether their liquid will be stable at low temperature, forming a eutectic, or possibly whether they'll form another compound that can be stable at higher temperatures. And really that follows a similar pattern of using elemental properties but looking at their differences. And this even goes further to more recent papers. Here's work from Chris Bartell at the University of Colorado, where they predicted the thermodynamics of different crystalline compounds using properties of the elements that form them. Here you're looking at different kinds of elemental statistics that can draw, such as the element fraction weighted means or differences. So all of these kind of follow a very similar tune of using elemental based properties, but this isn't the only way that people treat inorganic compositions. There are also intuition based features that are very similar to those handbooks of molecular property descriptors that you've seen. One good example of which is work by Kevin Laws from the University of New South Wales, where he's reasoned about how spheres of different sizes pack in space and use that to create descriptors that capture which compositions should form these particularly dense and stable clusters. And that actually has a lot to do with predicting which liquids are going to be stable at low temperatures and which will not, which will solidify at a higher temperature. Additionally, there are unique neural network designs, like what has come out of Reese Goodall and Alpha Lee's work just this past year, where they use concepts of those message passing networks that we've described earlier to be able to learn how different elements interact with each other within a compound, and use that to predict the properties of an entire composition. Further, instead of relying on a human's knowledge about how elements are different, there are ways of learning these directly from data, such as this Adam Tuvek paper, which studied how different elements are found in stable compounds. Some elements tend to have similar environments to others, which we can use to create features that capture those elemental properties without kind of any need for human intervention at all. And further, there's really cool work out of a group at Berkeley that showed how you can learn which elements are similar or not by using intelligent text processing algorithms that say capture how elements form different kinds of oxides and have different crystal structures, and those they found can actually, those relationships they found can also be used to build machine learning models for compositions of materials. And again, this, like Adam Tuvek, required no human input whatsoever, just, well, at least not directly. It learned from how humans describe elements in papers. We'll be learning a lot more about Math Scholar in one of our later lectures. Additionally, I've told you earlier that materials are really special because the way that they are processed and their structure can influence their properties. For example, we can take a look at this plot of what happens to aluminum alloys after we age them at high temperature, and you can note that their hardness can increase by a factor of 2 just by aging that material. The only thing, the composition of the material is not changing, just the processing is causing the micron and nanoscale structures to change, and you can see how that has a really marked effect on the kind of macro scale observable properties like hardness. And then of course there are materials like carbon, which depending on whether they form a closely bonded 3D structure or whether they form a 2D planar, can be the difference between something being graphite or diamond, again with just extremely visible different properties. And one of the key complications with modeling materials is you may get into trouble if you don't consider effects of properties in structure. I've had experience from this in my own work where we tried to design alloys that were processable using one casting method called injection molding, and we found that our materials ended up fracturing using this method and not using other kinds of casting techniques such as copper mold injection casting, which happened to be the primary way materials were fabricated within our data set. So because we didn't account for that difference between injection molding and copper casting, ended up yielding materials that cracked as we were solidifying them, which was the exact behavior we were looking to avoid. But that's not to say that all materials, all machine learning models that kind of explicitly ignore processing or structures are doomed to failure. There's really great work from Michael Gratois and others that illustrated how you could find new thermoelectric materials by only searching over the composition. They in fact found ones that are very different than existing thermoelectrics. And they did this by explicitly ignoring the fact that thermoelectric materials only have good properties within certain structures that are arrived at using very particular processing techniques. Ignoring all that allowed them to still find a good material. So that's not to say that if you ignore process or structure, you are doomed to failure. It's just that you have to think carefully about what your data set was comprised of, and you may expect surprises such as cracking and shattering materials when you try to synthesize them. And there are, of course, many ways for accounting for processing and how that influences the properties of materials or its structure. We can look at kind of 3 examples from the literature, such as kind of a rich history of using neural networks to predict how the structures of steels will change based on how you process them. There's also cool work out of Fordham University and I think a few other collaborating institutions where they could predict based on different processing conditions whether a nanoparticle synthesis was going to fail or not. And then finally work out of my own group where instead of accounting for the materials processing inputs as direct inputs like they have in Chatterjee and Recluglia, we simply partitioned our data based on processing technique such that we selected a model that was only trained on data using the processing that we were eventually going to use in our experiments, and that we ended up finding led to models with better accuracy in our intended processing technique. And then finally, there are ways for incorporating material structure at a variety of different scales. As we've discussed in previous lectures, they're a way of taking atomic scale structures of molecules and predicting their properties. You can repurpose those same kind of techniques for studying inorganic materials. And there are also some that explicitly are designed for modeling the kind of structures that form for inorganics, such as looking at the local environments of atoms using a technique called Voronoi tessellations that really require a structure to be crystalline in order to have meaning. And then finally, there are plenty of ways of using techniques borrowed from image processing to investigate the micron scale structure, which is well exampled by this work from Kondo and others that used convolutional neural networks to study ion conductivity in materials that differed based on their micron scale structure. So that's a lot of introductions of different ways that you can take materials and compute features from them based on different aspects of their structure. And I'm happy to report that there exists many different codes for helping you do this in different kinds of material problems. We've already used QML in one of our homework assignments, not one of our homework assignments, one of our practical lab assignments that show how you can take in the atomic scale structure and use it to predict material properties. There are also tools like PyNKS that can help you take microstructures and turn them into useful features. And then finally, tools like MapMiner that have a variety of techniques for compositions or even the electronic structures of materials and using them to create features. So really the point of this is that depending on the kind of needs you have based on what sort of data you are trying to model and whether that, say, differs based on microstructure or electronic structure, there may very well be a code that can already help you down the path of building a machine learning model. So with that in mind, one of the key concepts that you may have noticed has come up a lot in some of our previous lectures and especially in our discussion today on how not taking, say, processing or structure into account can lead to errors. To me, raises a lot of questions around how can I test my model to take these effects of, say, or intentionally avoiding some features of your model or some features of your data into account, or the biases in how you collected your data into effect really change how you need to validate your model. And what it comes down to is that cross-validation is still the technique that you're going to use to validate a machine learning model. It's really the only way to test the performance on a model using data that you have available. But the ways that you go about doing that can have strong effects on whether you'll get an overly optimistic view of your model's performance or not. And really what the knob that you have to turn in building a cross-validation technique is how I take my data and split it, say, into training or test sets, or take my training data and split it into different folds that I'll use for cross-validation when I'm determining the parameters of a model. And to give you two examples of where that can come into play, we'll look at some examples where people have found very big differences between validation and training sets, such as work that I've been doing over the past year or so on modeling the solvation energy of materials using message passing networks. And we noticed that if I used a validation set that did not take the size of molecules into account, I could see misleading results on which model I should use for making predictions on molecules. In particular, I found that one of my network designs had a much better performance on my validation set, which was composed of only small molecules, those with 9 or fewer non-hydrogen atoms. But when I start to validate my model on larger molecules, I can note that I get extremely large errors compared to a different design of network that, while it performed worse on those small molecules, did better on kind of the larger molecules, and even though it did worse on average across the board for the smaller ones. There's also a really fascinating paper out of Stanford where they showed that two different machine learning models, despite one performing better on a leave one out cross-validation test, ended up performing much worse, in fact worse than random guessing, on a test set that was pulled from a different population of data. In contrast, a machine learning model that was built on different features worked just as well on validation as it did on test. So this is, again, to go further example how you can run into very surprising issues like enormous errors on a model, on a validation set or a test set outside of your training population if you don't do your validation carefully. And there are a few different ways that you can design better validation algorithms that all are designed based on the concept that you want to mimic your data or the ways you partition your data based on how you're going to use that model later to, say, design a new material. One easy to understand example of this is using cross-validation for models that predict time series data, where generally you want to take these models and predict what's going to happen in the future. And if I use a standard random split or even a naive, even a more naive, just split based on the first 20, 40, and 60% of the data, I can end up with validation sets that evaluate my model's ability to predict both the past and the future based on some of the data, which isn't necessarily representative of how I'm going to use the model later. Rather, I'll want to, say, design a test set that only includes data coming in the future of those models I used in the training entries. Additionally, one way we often use machine learning models is to try to find new types of materials. And often the data we're training on has different subclusters within it. This is an example from Bryce Meredig, who is trying to predict new superconductors and found that we have very common or very similar clusters of data within his training set, and found that if he takes these clusterings into account, he can get markedly different results on cross-validation, and that could give him, say, help him inform which models are going to be able to find an entirely new class of superconductors, and say which ones are limited to being able to interpolate within clusters of existing data. Another way of doing this is not necessarily to rely on data-driven clusters, but I can take, say, my data based on different alloy systems, and knowing that I want to use that machine learning model to predict the behavior in new alloy systems, I could do a test where I say intentionally exclude all data from a certain phase diagram. Here I'm showing one where I removed data from the aluminum nickel zirconium system out of my data set, and then was able to gain some confidence in my model's performance by training it on all of the remaining data and seeing that it could pick up some subtle features within how this material system forms classes without having ever seen that data. So this wraps up my kind of introduction into machine learning for materials data. And the points that I want you to walk away with understanding is that what separates materials from molecules is that you need to understand how the processing and structure of a material may influence how you need to build a machine learning model. You may need to account for, say, how processing or structure influence the properties, or you may have to intentionally ignore them depending on how you want to use the model, but take that sort of behavior into account during your validation. Additionally, the kind of descriptors that one uses for building these machine learning models are indeed similar to molecules. You can build features based on the properties of each of the elements in that material, but there are also some more material-specific techniques like endpoint correlation features, which you can compute using PyMKS, that can capture the micron scale structure. And as in molecular machine learning, there are many codes like QML or MapMiner that might give you a good starting point for building a machine learning model on your materials data. And these would be the kind of tools that we're going to learn about in the practical assignments from GitHub. And you're also going to see and get some practice with developing cross-validation techniques that go beyond those which you can find in scikit-learn. This wraps up the lecture for today. We'll chat about it on Friday, next Wednesday, and you'll learn a little bit more about it on GitHub.